welcome to another episode of Robo Papers. Today we are super happy to have Yutong, who is one of the co-authors of this paper called Whole Body Conditioned Egocentric Video Prediction.
Nice to meet you. My name is Yutong. I'm a postdoc researcher at UC Berkeley.
This data set is wonderful. I was looking through this yesterday. So I suppose the way they set this up is they have the volunteers wear the area glasses, and then they have the whole lighting setup to do motion capture. But do you know how many scenes did they do this in, like this 3,000 hours?
Yes, I think although the scene, like
50,
for example,
50 scenes basically.
Yeah, but like, first of all, I mean, before I do any type of research, I would first start by watching this data set. Actually, like, for example, even in one house, there's like millions of different activities you can do. They were like playing with making the balloon animals, and they're like cooking. See, this is even outside. They were walking inside a car. They're watching TV. They're doing huge amount of things. The reason why we didn't use, for example, like the OpenX embodiment or the classical robotics data set here for training is because I think the OpenX embodiment is like a joint effort from different labs in academia. For example, this lab collect a bunch of data, that lab collect a bunch of data, and they put them together, right? But then the problem is you can actually see that, for example, one thing I observed, I remember there's a red ball in the data set, and every time I saw that piece of data, it's coming from the one specific lab in CMU when they're doing that specific task, and that's only when that red ball appears basically. So that being said, is the action space is not as diverse as human, for example. That's why I'm saying I don't think at this point, I think we already proved that the visual generation space is amazing, because visual information, or at least the videos, our visual world contains a great amount of complexity that allows the model that basically force the model to learn rather than cheating or finding or learning some shortcut. But in terms of action space, we need as diverse action space as a visual space or the linguistic space as well to be able to train something that's actually learning but not overfitting. So then I actually need and then humans are perfect for studying this problem because we just have really complex actions here. Right.
In fact, like Chris and I were just saying just now, like it's impressive that even with 3,000 hours, you can train something. Like it just feels like it may not be sufficient, given that there's 70 over DOF. But anyway, you should continue.
Because I think there's another difficulty in training this, makes this non-trivial, because most of the time your body is hidden. Egocentric video means like most of the time you cannot see your own body, right? So the model has to be able to infer from, for example, when we're walking, our legs are moving, we have this gait, right? Your camera is changing a little bit and you're leaning forward, whatever you see is changing. So in order to make this prediction correct, the model have to figure out the consistency between your action and your video. It's essentially a difficult enough task that you have to learn. Otherwise, there's no way the loss can go down. That's, I think, the other point of why it has to be egocentric video. Because imagine if the third-person video, then it's trivial in a way that the things or the 90% of pixels not changing, for example, in the background. Like you take me, for example, if you're looking at me right now, all the things is just my head and my mouse is moving, right? The actions does not directly correlate.
But yeah. I mean, we have things like Genie or DreamGen or whatever, which have all learned these kinds of things without a direct action signal, right? That they learn it from third-person video. Right?
Yes. So to generate a video, it's not difficult, but the key of the role model is your action has to be able to control it. The controlling part is difficult. The pixel generation is perfect. Right. Like, for example, just because you're giving a bunch of text, you can generate video does not mean that we can alternate like video. I can actually grab something up, right? There's a difference. This is if I'm making myself clear. The visual data quality does not guarantee the controllability. Right.
So Yutong, just to double tap on what exactly you say, right? Just to clarify. So what you're saying is that because of the fact that this data set is egocentric video, and obviously egocentric video, you literally don't see your own body, but by forcing the model to learn based on egocentric video, the whole full body, you actually learn something else, which is a controllability of the action, is what you're saying.
It's a non-trivial task.
Okay, got it.
It's a much harder task.
Got it.
So, right, and this is basically architecture. We're using a autoregressive diffusion model. So basically, it's quite standard. It's we have some videos. We extract the frames. I can play with it. Okay. So first you have a bunch of videos, and then we can randomly pick 2 frames, and then we extract the features from this encoder that is the VAE of the stable diffusion. So you get a bunch of tokens. For these video frames, you get a bunch of tokens, and you also have the ground truth action provided. And then, so they have a bunch of tokens. You have visual and you have your action tokens as well. You add some noise. You have the DIT block. And then you try to perform this denoising task, right? That is how diffusion model usually works. But then here, because we need to do the prediction task, so this attention is actually causal. We're using causal attention, so the model only attend to past frames so that it predicts the future frames. And then here the action is we use eta-ln to directly condition the action into the eta-ln so that it can control this. I think eta-ln's first is adaptive layer norm is first proposed in DIT, the original DIT paper, and is proven to be very useful to understand the scale and the shift in the temporal in temporal space as well. So the action can so the action condition is proven to be very effective if we're using this technique. So this is how this model architecture looks.
You don't get to ask like random time skips, like concretely, like
yes.
What is the range?
Yes.
Typically you guys try.
So I think I put it here. Okay, I didn't really put it here. So the purpose of the random time skip is because sometimes I think only predicting the next frame would be too easy, in a sense that imagine like if I only predicts what's gonna like the next 1 frame, for example, the movement is relatively smaller than, let's say, like 4 seconds later. So then the model's task will become easier. And we want to make sure that the model attend to both the short-term dynamics and longer-term dynamics. And also the task is hard enough. It's not trivial. So basically, then we're basically trying to we randomly select how much into the future the model going to predict. And because the action, you can actually calculate the action based on the different time skip. You can calculate the difference between the actions.
So the time skip meaning, so this is just like so it's like going to be like a full body joint state delta from the current frame to like some random amount of time into the future. But what if it's like, but how do you get that to handle like granular motions, like grabbing a handle or something? Like if you predict far into the future, the next state might not be meaningful. Does that come up?
I think it's that's why it's random. We have both short term and longer term. It's not like we only do long term skip. It's like mixed to get a balance, basically. Yeah.
So sometimes the longer skip may not be meaningful or maybe missing information, but what you're saying is that it just comes out, like it doesn't matter because you train it long enough, basically.
I think sometimes the longer time skip helps in a way that it captures the longer dynamics as well. Like for example, it's useful both ways. So
I guess I'm saying like if I'm grabbing this object, right? I guess if I'm grabbing this object, like, and then I predict, and like for a second in the future, I'm holding it up in the air, then my hand is going up here because it's not doing the grasp in the middle. Right? That was the thing that was confusing, I guess.
Oh, yeah. I mean, so then, you can imagine that it has both random time skip, meaning like there's 0.5 FPS, there's 4 FPS, there's 2 FPS, there's 1 FPS. It's like data augmentation in a sense. It have both fine grain and longer term as well.
Okay. So
because human motions, like
so
you just said,
what would you consider a longer term? Like literally like 10 seconds? Not that long, right? What is so-called in your mind longer term? What is some of the longer time skip?
That's why we have random time skip, because for example, even for different human, the way I am grasping this apple is probably going to be slower, or that other person grasping this apple going to be faster, right? And also for different tasks, for different skills, like for different all sorts of motions, or even different people when they're executing the same task, it could take them different amount of time as well. It's hard to predefine. That's why I think you need to attend to both shorter term and longer term at the same.
Okay. Cool. Okay.
So we can see some results. Like for example, later from now I'm gonna show a bunch of action rolling out result. Basically how this action rolling out works is if I provide past frame, current action, and I told you what should be my next action, and the model rolling out the frames in a sequential way. So for example, in this case, this person is trying to go upstairs. Okay, so this is called, I'm gonna show the visualization. So we're gonna initially start with showing some atomic actions that contains some navigation, some hand movement, and later we're gonna show more, focusing more on the hand, the interaction between the hands and the object. For example, this is moving forward. You basically give a chain of every time you give the next action, and the model trying to predict the information, the visual information, and it's using its own prediction to keep predicting. This is moving forward, and this is rotating left. We're basically giving the pose, so it's not like I'm giving the text. I'm just putting the text here, easier to understand. And this is rotating right. You can see this is actually a restroom, and there's the person that is outside the door. It's kind of creepy though. This is moving left hand up. I think this person tried to hang up something. And this is moving left hand down. This is moving left hand left. You can see here is like trying to organize some clothes. This is moving left hand right. This is moving right hand up. I think in this kid's trying to grasp something.
Curious about this. So you're saying moving left hand up, and so earlier you were talking about how the human body was not these big high level actions like moving left and right and so on, like in Genie. Right? You're saying this, which is right. Like obviously that's the wrong way to view it.
Yeah.
So so when you say move right hand up, what does that actually mean then? Is that like moving these joints by like half a meter or something?
Yeah.
Like concretely, what is it?
Yes. So basically, I mean, I have to evaluate, right? I want to evaluate in a way that and provide some numbers on it so that we can know how much it's performing. And we basically, in terms of the evaluation testing dataset, we collected a bunch of actions in the evaluation dataset that contains the significant movement. For example, if this human have in these actions, the action is going to be the whole body action for sure. But then, for example, if in that clip, it contains a significant amount of moving right hand to some centimeters, for example. And then we basically like extract that clip and put it in this category so we can provide a more concrete number. Otherwise, it's hard to evaluate.
Yeah, makes sense.
Yeah. Okay.
Do you have any tests where you move like the hand like 30 centimeters up versus 20 centimeters up versus half a meter up? Or did you do anything like that? I'm just curious as to how granular it ended up learning.
I think it's we have some result later. I can show you.
Okay, cool. No, sorry. We don't want to get ahead then. Sorry.
Yeah. You can move right hand down. Here is actually trying to write something on the whiteboard. It's kind of funny. You can move right hand left, move right hand right. Here is like it's actually open the door. Okay, so here is some counterfactual control. If I'm given the exact same input, but I'm trying to move my hand differently. Like for example, here I feel like I probably should visualize it a little bit better. It's hard to see, but this is moving.
Yeah, I can't really make those out.
Yeah. It's fine. It's fine. I can.
Sorry. No, sorry. Just ignore me.
It's basically, as you can see, from same input.
Sorry, go on.
Oh, you're just moving the hand differently. And it just shows like different counterfactual. I think maybe This case is easier to see here. Like, for example, you're kind of moving your hand differently. Like, for example, here, you're moving your hand up, you're moving your hand left.
Cool.
So that, yeah, I think this is, in this case, a hand is like clearer in terms of the background. So you can actually see that it's moving towards different directions.
Cool.
Okay. Sorry, what's the question?
No question. Sorry.
Oh, all right. Okay. And then I want to study something that I think is also interesting. Some semantically similar actions. Like, for example, open the drawer. But like, let's see, like, open the drawer, for example. In this case, open the drawer, and in this case, the drawer's location, and including how people are reaching to it, and how you can see the position are totally different. Like, for example, here the drawer is on the bottom right, and here the drawers is on the left. It's actually on the side. So although it's something that's semantically very similar, for example, is all open the drawer in the text space, the actual action, the actual consequences could be very different. Because here's like, something that is not easy to be simply expressed or controlled by just semantic space. And then this is close the drawer, and this is like reaching out to an object. Here, this person is trying to reach out to the object that is on the shelf. In this case, it's like, in this case, is reaching out an object that is, I don't know, like from the top to the bottom and trying to reach an object inside the drawer. And this is trying to this person, if you take a look at a small human here, actually need to bend over and try to reach to the yellow block. And this is also reaching out an object. This is actually funny. This is actually taking out the books, reaching out to an object. It's actually all looking different, despite semantically very similar. It depends on the context and the environment and the body pose. And this is walking downstairs. This is a different stairs, but in this case, you can see this human's hand move. Like when we're walking downstairs, we can't like hold to the beam. And this is open the door. This is, I think this is like door on the cabin. But in this case, this is actually interesting because this is also open the door. But here, the door is pushed open. Mm-hmm. So you kind of like, this is a totally different way of interacting with the object. That's why it's harder to make a classifier into that, I think, because action space is actually very difficult. This is like push open.
Sorry, you don't. So in this case, opening the door, right? So I suppose the world model is just dreaming up what is behind this door. It could have been open the door to a forest or open the door to a bedroom. In this case, it decided to show you a bedroom. Yes. Interesting. I wonder if you have tried like the reverse, like the action, open the door and then close the door. Like I wonder if the world model has some consistency and then you open the door again, is it still in a bedroom? Now it doesn't, I suppose.
Actually, I think I do have it. I actually already, like, this is like close the drawer, right? See, this is close the drawer. And I think I have the same open the drawer here too. I was playing with it.
I see.
Because essentially what this world model is learning. The world model is, I got another question that I think is very interesting. So when I was given this talk last week, I was asking a question like, for example, here, if our hand is in front of the drawer, for example, why? And then I for example, I push my left hand left. Technically speaking, it should open the door, but it could also be the fact that I'm just making a fake action. I'm just like waving my hand in front of the door, not trying to open it. How would the model distinguish? I think my understanding for that problem, similar to what you just asked me, is what are we expecting from the video models or the world models? It's some sort of prior. Prior meaning like most of the time, if I'm putting my hand on the door and like executing that sort of action, this is the most probable thing I would do. And for example, the way if I'm drinking from a wine glass, why would human approaching to the wine glass in a certain way that your hand is posing there? For stable, it's for some like temperature. We don't want to use our hand to directly touch the wine glass, for example. There's a lot of cultural things, a lot of these things as well. So I think world model, the purpose of that is trying to learn some sort of prior that could be a little bit 3D, that could be a little bit cultural, that could be a little bit efficient, or how humans execute things. So again, like I could not know what would be exactly in the drawer just from the video itself without without specifying it. But it would generate something that is most probable in this case, in this scenario, most probable answer. I think there's going to be something in the drawer. But in terms of actually, if you actually wanted to be used in a more real life environment, I would suggesting something like a closed loop control. You're constantly giving new observations and predicting, new observations and predicting. I think that would solve that problem. Do that make sense? Yeah, right. And then I tried some all of these distribution actions or something that's not so usual. Like this person's trying to jump around, and this is like pumping a balloon, which has never appeared in the training set at all. This person's trying to hold onto the ground and try to stand up. And this is trying to do some sort of folding. I don't think, I think it's hard to judge whether the folding itself is correct or not, but I think it's trying to do some foldering-like-ish kind of movement. Right, and I have some longer sequence rolling out result as well. I think unfortunately this is kind of stuck. I can play with in the actual, we have a project page, but you can already see like this is the whole scenario is very diverse. It's very have a lot of different scenarios and a lot of different actions. Hopefully here this is okay. Nope. You get the point. It's a lot of different
it's okay, yeah.
yeah. Okay. I even have this foosball. Right. And then we also have some quantitative results. I think the thing that I think is worth discussing is something that's more important. What to compare. Before I talk about some concrete number, the important thing is what to compare. Because right now it's basically providing a new type of control, right? Like compare with text-based control or some different levels control. It's just providing different type of control. So then the one thing I tested the first is how does action actually influences vision? In a way that does my action condition is actually useful or not? I think this is also a question Chris was trying to ask. Like I can also just by predicting pixels based on the pass frame, there is no guarantee that the action is actually doing something. Right? So one experiment I do is I try to give the model different actions. Like for example, 0% means I try to mess up with the ground truth action. 0% meaning like I give the model ground truth action. 100% meaning like I give the model completely random noise actions. And I try to study how would that actually influence the video you're predicting. So here you can see that the x-axis is like how much noise I'm given to the action I'm trying to condition the model, and the y-axis is the predicting predicting the vision space. We are using DreamSim and Matrix, but here is basically means like the larger the number is, the more error the prediction is. So here you can see that basically the ground truth action gives the best visual prediction, and if you messed up with the action, 100% mean like it's completely random action, it would give you completely random, not random, it would like heavily influence your vision prediction as well. And we also try to compare with text condition model. Like in this case, we basically find videos that is have some more fine-grained hand actions, like some manipulation actions, and I basically try to see if I can get Cosmos, like the text condition type model to do the same thing. It's actually very, very hard, because if you take a look at the example, only hard for the model either to understand or to interpolate or to execute. So I guess this is why when you actually wanna provide more controlling space. I think text is great in a lot of level, means it's very high level. Semantic is perfect for using the goal, but in terms of more fine-grained control, I think it's gonna just simply harder. This modality itself is harder to control. Yes, and then we've tested the generation on both like camera poses prediction and also on hand pose prediction, basically some evaluation that is beyond pixel space, but also how good we use VGGT to try to like to try to see if the reconstructed video frames have correct camera pose or have correct, for example, hand pose, hand gesture, and all this kind of things to try to prove that it's learning something not just correct in pixel space, but also in other space as well. I mean, I have a lot of numbers, but I think maybe I could just skip the most of these things.
Yeah, we can. That's okay.
Yeah. So then, right. And then you can also use that to do some sort of planning as well. I think Michael was asking me this question. So basically, now if we have an action conditioned video prediction model, what you can do is you can also provide the visual as a goal and try to let the model search which action could lead better to the goal. I think this is kind of something humans do as well. For example, I know that if I'm, I don't know, breaking out from the window and jump from the 8th floor could make me dead. So I'm probably not going to do that. So by imagine what's going to be the future different rolling out, you kind of also understand how to choose actions too. So you can do, we didn't do too much like training a policy, whatever on top of it. We initially just did something more straightforward, like doing some searching to try to search which actions can you do. But I think that's something else you can do on top of this kind of like world model too. Like here, for example, if you show the model the goal is to approach to this thing, the model will say, okay, maybe I can try to move forward. Okay, that leads to here, and move left, move right. Now, obviously, move forward give me the rolling out is more similar to the actual outcome I'm expecting. So in this case, I can actually choose. I would know like which action to choose. So this is some like NPC control for the basic plan.
So how do you tell which action, like how do you decide which result it is? Like how do you generate the score?
Yes. So here is the most naive way, just sum cross entropy. But you can also adopt, I think people try to adopt something more complicated, like a VLM or whatever. We just use the most simplest thing. Yeah. Okay. I think that's basically
so actually
it.
So Yutong, actually just on this one. So I guess like what you're pointing towards just now is that the way how these world models can be used like in robotics, let's say, is, for example, at inference, you can let the model just dream up using something like this and then plan accordingly so that it's but so this is basically use and inference, right? Is that how you think about it? At least the way you present it now.
Yeah, exactly. Because the world model is basically like a simulator in a sense, right? It's like simulator. So you can change the action, you have different observations. So then later in the second stage, you can either do search or you can train a policy on top of it. It should be similar. But I think one thing that in my mind, something need to be adjusted compared with the traditional simulator is there's a lot of things that a video can provide we want to make use of. Like, for example, a desk could have only that much way you could interact with it. In a sense that if I show you my pose or if I show you my view, the current observation of the desk, for example, it's not like my actual action space is the action space is not like every one of my body joints can be act in some way. It's only that many of ways you can interact. As the actual action space is actually smaller than the degree of freedom. So I think in terms of designing more complex policy, this is something we need to think about. How to fully make use of the world models, like the learned priors and everything, to design a better policy.
Yeah. Okay, that makes sense. Yeah, one thing that I think is interesting is that like there's I really like the idea of the world model as this like differentiable simulator, like you're saying. So I can use this to do like NPC style planning, right? So like it's a really cool idea. But there's this other whole set of like we had John from NVIDIA Gear Lab on recently, and this is like there's a second way people use simulators, which are these language condition simulators. Like they used Juan, I think. Right, or you could use Genie, or you could use like or not Genie, but Veo is the other one, the other one. So like, what do you think of? What do you think are the pluses and minuses there? Because like those obviously they generate like they're a little bit more data efficient probably because they don't need so much like motion data in a particular space. But what are your thoughts on? But on the other hand, they don't get the granularity. What's your opinion on?
Yeah. So I think, I
don't know.
think I actually have another example that's kind of interesting, and maybe I can share.
Yeah, because okay, well, while you're looking, I guess one thing that I've always thought was cool about this kind of stuff was that like there's the potential for much finer grained tweaking.
Yeah.
I assume,
Yeah.
like your example of it,
Mhm.
23 degrees, right? Is so it's nice to see. I was
Yeah.
yeah. Do you have any? I guess.
Yeah. So
Uh,
previously, when I
yeah.
was trying to, I think I had a very interesting example in terms of the difference between the modalities. Like, for example, if I asked you to describe the color here, and I asked you to describe the pose here with natural language, it's just simply harder. It's not like it's impossible, but it's not easy. Like, if you take a look at this picture, right? It's just not the easiest thing to do in terms of even describing is hard, and not in a way that you can describe the other person can reproduce. Right? Like, if you like, how can you explain this lighting and my movement in a way that you can reproduce that? It's just not as easy. That's why I was saying, like, I was when I was trying to some fine grained actions, if I want to write this, essentially it means I need to move the hand slightly upward the 23 degree. What does it even mean for a language model to execute? It's just harder. But language, again, it has its own like ability, like longer term planning or longer term goal, like very specific specifying from saying longer range. Yeah, they just have their own, each have their own advantage, I think. Yeah.
Well, I think one other advantage in this case is that this is already conditioned on control, so you already get that. I mean, that is actually like steerable. Whereas the other one, you have to reverse, like figure out what is infer the control, and it's not going to be precise at all, right? So you have the opposite problem, I think.
Yeah.
So in a way, maybe this is way more like just plug and play for actual inference, doing inference. Okay, dream out the scenario. Then now but I already have the action, right? So yeah. I
I
think.
mean, one use case I can think of is like, since we have this ground truth pose with like actual the kinematics, so then you have the location and you have time, you can calculate speed, you can directly do some retargeting. I think there's a lot of humanoid papers is very advanced in retargeting. They did a very good job. Right. So it's easier to do that when you have a concrete action space.
I'm curious, like, could you speak to the type of compute that you need to run, I guess for you to do the training and then eventually like for you to do inference? What kind of compute are you talking about?
Yes, I think we were using around 32 H100s and training for a couple of days for 1B model. I do not know the exact hours, but yeah, I don't think it's that much. I mean, we trained a 1B model from scratch. It's actually not that heavy in my point of view. It's not impossible, at least. I mean,
Yeah, it's actually fairly small. That's it.
We didn't have the resource to, because we want to publish, so we don't have the resource to train on even larger
32 H100s is a lot to say we don't have any resources.
It's I think it's a collaboration.
But it's just a couple days. Fair enough.
Yeah, it's a collaboration with Meta. It's not like we could afford it in the lab as well.
Yeah, fair. Sorry.
How about inference? How about an inference?
Inference, I didn't really log it. I think I probably have some data, but I probably need some time to get it out. I think. Can I? Do you want me to?
Because I'm just trying to get a. I'm trying to get a handle on like the practical use case that we just spoke about, right? Which is at inference, you have the egocentric observation as an initial state, and then you're trying to maybe that's an image goal, and then what is the condition? So, but to basically dream up different scenarios and then pick the one that will get you to the goal that you want. So that running that different scenario, is it something that can run on a simple like consumer grade GPU? I presume.
So I think right. I think it can. I think when I was playing with the models, I think if I'm running locally on, but I never really get one single GPU to myself. That is alone. That's fully empty. But like it takes like a couple seconds to inference one image. But that's just on one GPU. I think in order to basically use it, I think a lot of paper right now is doing real time interactive world model, there's a lot of techniques to really speed the inference time up. I think, and a lot of actual robotics, they actually would connect their robots to a cloud computing. It's not like they're just using attach a GPU directly on the humanoid, for example. So I think we definitely would need more technique to make it real time, but I think there's already a lot of great work trying to make this whole thing in a real time interactive way. But right now, in our case, yeah.
Sorry, you said it was 1 billion parameters though, right?
Yeah.
So that would be 4 gigs of VRAM. So that would fit very comfortably on a consumer GPU. To Michael's question, I think
Okay.
But it's not. But I guess it would be very slow if you did that. Is your point?
Yeah.
That's fair.
Yeah, so I guess what would you say, Yutong, is something you would like to continue to see, like as a follow up to this work? What would be something that you want to really try? Like, would you go and ask Meta, okay, maybe just give me 10x of like a Namaria like data set? Do more, or just the data side, or something
else? First of all, if they're gonna do larger scale, I don't think I would have anything to do with that anymore. That's just a side note. I think the difficulty is right now, like especially when everything is scaled up, there's a lot of things I observed that is interesting, but they do not release any technical details.
That's fair.
And a lot of papers, but then limited by their scales, and there's a lot of so they limit the problem they can analyze. So there's a lot of just problems not very first principle or not very essential that I find it interesting enough. But I do think the problems are internal. It's not like new technologies would obsolete some problems. I think the problem I just described would remain interesting.
Cool.
It's not a very good answer, isn't it?
Yeah.
It's all right.
I do find like Genie 3 to be very cool as well, but I have no idea how it's done.
No, I agree with that. It's like there's the at least there's a couple open source video ones which I think are somewhat impressive, right? But like the data's not open, so who knows what's going on, right?
Yeah. Mm-hmm.
Yeah, actually, that's another question, maybe a last question from me to you, Yutong. Like, I think it strikes me that especially for world models, kind of research, it's just a different orders of like resources required to even start, right? The fact that you have 32 H100, I don't know which academic labs have.
That's a lot of compute.
And that's just as a start, right?
Are you sure we're gonna put this on the internet? Please don't put this on the internet.
No, but I'm curious, like, to do, let's say, to do more world model research in the open, like what can researchers still do in the open, but despite, let's say, pretty hamstrung on the resource side? Do you have any thoughts?
Yes, I do. I think first, I think this is questions 2 level. The first level is what is a world model? It could be like action condition video prediction as its current format, but in a better way of understanding this problem is what kind of humans, for example, or like small animals all have some sort of, I think the psychologists assume that they have this small scale of predictive model in our mind. So basically we are able to anticipate the future events. Like I said, right? If I'm trying to break out from the glass, I know I would die, so I will not do that. You kind of have this constant, or you have this common sense, or you have some coherent understanding of the world, so you can use it to, either for planning your actions or either to do something. So right now, the problem is, I think to answer back your question, I have a paper I like. It's called Potemkin Understanding of the LLMs. So basically it's trying to say that LLMs is good at, for example, like knowing what is the concept of a haiku. But then if you have to use a concept to do something, suddenly you kind of find it's kind of starting to break apart. In a way that, how can we examine whether the model are just learning something on the surface? It just appears correct, or it has a coherent understanding of something. Like, for example, if I cut an apple, the next moment it should be like the two half of the apples, something, right? How do we find out that? Does a model start to learn something that is more coherent or start to build something like an internal world model like humans do? I think that's a very important question as well. How do we examine that? How do we call BS? Like, for example, even if the model generates very realistic videos. I'm a believer of video generation too, but at the same time, we also need to examine it.
Yeah.
Yeah.
I think to your point, like this is something I've been thinking about. I call it mosquito intelligence, because like I can never catch a mosquito, but you look at a mosquito, like it's probably running at 0.1 watt or even less than that. So whatever intelligence it has, it must be a super small model that is super extremely energy efficient. It cannot be a 1 billion, you know. So there is something that he has learned about the world that makes it impossible for me to like kill the bugger. I think maybe that's
the argument for passive versus active. I do feel like active, one advantage that can have is a more efficient. You have kids, I don't, but I was told that when kids were younger, they're kind of like their learning have different stages. Like if they see something new, they start to play with it. After a while, they're good at playing with these toys, and they immediately lost their interest and moved to another thing and started to play with it again. So that means in a very relatively short term, they master at this skill and they move to something else. This is something called a curiosity driven, for example. It's obviously a much more efficient learning paradigm that our current model doesn't have. That's why it's heavy. It's right. So maybe if one possible solution is if the things can be interactive, maybe we have a chance of building up something that's more efficient, or the learning paradigm is more efficient as well, not just model size, the number of data, right? Because you know what you're gonna bad at, what you're good at, so you actively search things you're gonna practice.
So I think this is actually a really cool direction, especially with the curiosity stuff. So one of the things you were saying earlier was that you think that the curiosity is defined as basically when our world model is incorrect, right? And so like, are you thinking that you would like to use this stuff for like reinforcement learning to try to put together curiosity driven exploration, like co-learn a world model as you
I am thinking and trying to do something about it. But I think the difference between reinforcement learning is you pre-design you preset some task. Like, for example, at least from my understanding, the whole point of exploration is to explore the unknown problems. Like, let's just say that if I know, like AlphaGo, if I know that what kind of task I'm going to solve, and I know what is the rule and how to solve it, I am sure that with enough searching, the reinforcement is gonna beat human. I'm not doubting about that. But I think the most difficult part is to determine which are the things you're not good at yet. So that being said, we need some sort of feedback, but in my point of view, it's probably not something as at least a current reinforcement learning format, probably something more unsupervised.
Right, but like, so what you were saying earlier, to go to but like, I could say that my reinforcement learning problem's objective is to minimize prediction error, right, on this world model learning, right? In that case, like, that's probably the child's reinforcement learning objective, right?
I don't know about that, Chris, actually. I mean, if it's purely just to minimize, then you will never explore. I think the thing about curiosity, to me, I don't know whether that's the right way to say, but is like the reward function is undefined. You are just exploring for exploring's sake. So how are you going to define a reward function?
But how do you know what's boring? How do you know what's interesting to explore?
I don't know.
I think it's prediction error, right?
Prediction error, yes. Prediction error, yes. But also, I think Alice and Gopnik have these things called empowerment. Like, if, for example, I'm good at something good enough, I'm getting bored, yes. But also, if I can't get control over something, I give up too. There's two levels of giving up happening here.
But isn't that both prediction error? Because like, if I'm so good at it that it always succeed, it's boring. If I'm so bad at it I always fail, it's boring. Because they're both predictable.
Well, but then there are also those weird folks who will, okay, I suck at it now, but I'll just keep doing it because I just want to improve at it. But even that is still, I still feel that there's something about the framework of RL, like there's a reward function, and what if that reward function is largely undefined for certainly some people? Why do you explore? Like, some people, why do you want to jump off a building and try to fly on one of those wingsuits? You're likely gonna die, but there will be people who just want to explore. What is the reward function?
Excitement, or I think they probably don't care about death that much like we do. Each person's loss function is probably different.
We all have different hyperparameters.
Yeah,
true.
Different everything.
Yeah. Okay. Well, anyway, fascinating discussion. Thank you so much, Yutong. Yeah, it's really cool work. I think, I mean, and good that you wrote this paper because I didn't know about this data set. I think you make great use of this data set, and I think that this is a perfect paper to go with the data set. Yeah, definitely. Yeah, looking forward to your next one. All right, Chris, what have you learned?
This is some really interesting work on doing action conditioned video generation on probably like the highest dimensionality that I've seen people do this for, and on a really cool data set with like really rich, like massive amounts of human egocentric action data. And so, yeah, I think what I think is cool about all this is that like these kinds of like it's kind of pushing the limits of what these world models can do, right? Like what did you think?
Yeah, I mean, I'm interested in the practical use of it, right? So as we discussed just now, I can imagine it being useful for like just imagining like at inference, like okay, like just imagine different paths and then figure out. But the way she set it up is the actions are already, in fact, it's an input to the world model. So which means that you already get the exact action, like you don't have to. I think the other way that, like for example, DreamGen has they only purely in the vision space, so there's no action, so they have to use something else to infer the action back to right. So I wonder which one is maybe that's trade-off in both, but I think that's how I think like world models maybe could be used. But towards the end, we also discussed about this thing about whether the current iteration of world models, is it like an extreme overkill? Maybe again, it's the mosquito intelligence, right? Yeah. Do you really need to like predict every pixel in the world in order for you to execute in the world? A blind person have pretty good like physical intelligence, like embodied intelligence and hearing and all that. So,
I think part of the appeal is like is that working with simulators is kind of sucks. It's hard to do, getting them to work well. And so like
you mean classical simulation,
any kind of simulation,
the many skill,
so, like, for robot planning, right? Okay. For foresight. So like this is why we keep mentioning this like data-driven simulator term. I think Yutong mentioned it earlier, which is kind of nice because what like the idea being like I can just throw a bunch of data at it, and then I don't need to do all that, and I can represent all of these cool tasks. And because it's action conditioned, that means that I can actually roll out different possible futures, and I can see which one works the best. And like as opposed to like what say DreamGen does, or some of the other ones that we've seen, which are just basically they're generating data for an imitation method, so they're not doing the data-driven simulator part really, right? They're just like constructing new examples for you basically, and like so I think that part's kind of so like you couldn't really replace that, right? I think, but there's questions as to what kind of fidelity it actually achieves, which I think is always the tricky part with these. Like, can you actually can it really tell the difference between me executing this trajectory and executing this trajectory with like my elbow slightly lifted? And is it going to really understand those consequences? It feels like to me that the amount of data you need there might end up being like nigh infinite, but I don't know. It's very cool. What do you think?
Yeah, I mean, I guess, I think definitely this is, I mean, the reason why we have so many episodes on world model is because like, there are a lot of cool papers coming out that's related to world models. And I think they are starting to be coming up because like we have data and also we have compute. Well, at least in some labs.
You need a lot of compute. Yes, that's the other thing, right?
Yeah.
Well, yeah.
So,
cool.
I
mean, I think.
But yeah. Yeah. Sorry. Yeah.
I mean, my philosophy on a lot of this is that some amount of all of it'll be helpful. Like we just need it'll be like a little bit of everything. But yeah, anyway. Cool.
Yeah. Probably cool. Yeah, use a world model co-train with some real world stuff and then.
Right. Yeah.
Okay, cool. I guess till the next time. Yeah. Okay.
Yeah.
Cool.